theorem. Our goal for today is to use that theorem to solve some questions. Again, something that we did yesterday, the theorem that we had yesterday actually was one of the most fundamental theorems that we have in calculus. As I explained at the beginning of this semester, my goal in this semester is to teach you 5 important fundamental theorems. In calculus, we have 5 important fundamental theorems. Actually, you have seen one of them, fundamental theorem of calculus in Calc 1. This semester, we want to see 4 more, and change of variable theorem that we had yesterday actually is one of them. That's really, really important theorem and very, very helpful theorem. So, then without any more explanation, let's start. We are in section 12.8. Then we will start by one example. We will start by one example. So let me see. Then evaluate the integral r x y dA, where R is the region, where R is the region, where R is the region in the first quadrant, in the first quadrant, bounded by these lines: y equal x, y equal 3x, and xy equal 1, xy equal 2. So evaluate this integral of xy dA. So on R, where R is the region in the first quadrant, bounded by y equal x, y equal 3x, these are lines, and xy equal 1, xy equal 3, these are hyperbolas. So see, first of all, let me graph this region to show you here why we need to use change of variable. This is xy. Then if I graph this region, see, you have 2 lines. One of them is this one, y equal x, and another is this one. This is y equal 3x. Y equal 3x. We also have 2 hyperbolae. One of them is this, xy equal 1. This is xy equal 1. And another is, so let me see, suppose for example, 1, 2, another is this is xy equal 3. You know that these 2 so you know that these 2 have 2 branches, but since we just consider first quadrant, then I graph them in the first quadrant. This is a region which is denoted by R here. Then R here is this region. So then what is my goal? My goal actually is to integrate on R. Then this is R. As you can see, R is a very bad shaped actually region. It looks very a strange region at least. Then here, when we have region like this, when we have some kind of strange bad form region, people prefer to use change of variable to make region nicer. Then one reason that we use change of variable, because we want to integrate on a nice region. Nice regions are, for example, circles. See, for example, ellipses are not nice. Circles are very nice. Then the nicest region that we have in a rectangle, for example. Then if you have a transformation which can be used, that transformation, and convert this region into a rectangle, it would be fantastic. Why? Because integrating on a rectangle is very easy. As all of you remember, before the break, when we started the concept of double integral, I started this concept by integrating on a rectangle. So, mark, so, on the top. So let me check one. We have okay, 1 1 and 1 3. So yes, Mark, yes. Sorry about that. This is 3, this is x. This is 3x. Yes. Sorry. Okay, yes. Sorry about that. Thank you. Yes, this guy is x, this guy is 3x. Thank you. So, see, you have, okay, again, as you remember, I started this chapter by integrating on a rectangle. For a double integral, integrating on a rectangle is really nice and very easy because all bounds are constant. As you have seen after the break, integrating when bounds are constant is easy. But here, when we have this kind of bounds, since this region is very bad region, bounds are not constant. If we can find a transformation to convert this region into nicer region, will be very nice. Finding that appropriate transformation sometimes is not easy. But here for this question, one transformation is given. See, the transformation is this one, x equal to u over v, y equal to v. So, see, we want to use this transformation, and by using this transformation, we want to know that what is the transformed version of this shape with respect to this transformation. I was asked several times when I teach Calc 3 that how do you know that which transformation is appropriate? Another question which can be asked is there a unique appropriate transformation? For sure, we don't have any criteria to say that which transformation is the best. After solving different questions, you can find out what transformation is better than others. Another thing, we don't have a unique appropriate transformation. It's possible that we have 2, 3 different transformations that all of us actually work perfectly. But something that I can say, when I was a student in Calc 3, I had this criteria for myself. If you have a transformation such that by using that transformation, you can convert curves into lines. If your lines are vertical or horizontal, the best. But if you have a transformation which can convert curves, see these RCR, look at these blue curves, these are curves. If you get transformation which can convert curves into lines, that transformation is good. But again, finding appropriate transformation sometimes is not easy. For this one, actually, this transformation is given. I want to show you why this transformation is an appropriate transformation. So any question, Bob, up to now? Any question? Any question? Okay. So then we will find the transformed region of R. Then we want to transform R into another region by using this transformation. You have x between u and v, y between v. So, see, these are your shapes. Then you remember yesterday I solved an example like this. Your goal is to find the bound, the appropriate bounds by with respect to this transformation. Okay, so what do we have here? Here we have 4 bounds. Then let me denote these bounds by, for example, I don't know. So this guy by, for example, R1, R2, we have 2 lines and we have 2 curves. Then this is R3, R4. Then R3 is what? XY equal 1. R4 is XY equal 2. Okay, so then we want to know that what is the transformed of this. So then let's see, in R3 and R4 you have X times Y. Then I will multiply X by Y. Then X is U over V times V, right? Because X is U over V, Y is V. Then you are multiplying them. Because here in R3 and R4 you have the multiplication of X by Y. Then here I will multiply X and X by Y, but I will replace X by this function in terms of UV and Y by this function in terms of, okay? Any question? Any question? Comment? So V and V will be cancelled, this is U. Then X times Y is U. So see, R3 and R4 can tell you the bounds between R3 and R4 can tell you the bounds on R3 and R4 is U between 1 and 3. And see, my goal again, what is my goal? You have bounds on X and Y. Your goal is to find bounds for U and V. And so here I could find a bound, one bound at least for U and V. Is it okay? Is it understandable for everyone what we are doing? Everybody is following? Okay. Question? Guys, don't be shy. This is not easy. Then don't be shy at all. Any question? So let me see. Everybody is here. Sorry. Moment. Yes. Okay, good. So, see, you have X times Y, then, good, nice question. So, Alex, where did X equal UV and oh, okay, Alex, very good question. Actually, see, this transformation actually was given. It means here, since this teacher is very kind man, I gave you this transformation. In the test for some questions, appropriate transformation is given, and sometimes you have to find the appropriate transformation. For this question, since we just started, then I gave you the appropriate transformation. We will solve a question which transformation is not given. So you're very welcome. So, okay, any question? Any other question? Let's see again, this transformation actually here is given. Then in the test for some questions, the transformation is given. Sometimes transformation is not given. You have to find it. Okay, so see, because here you have xy equal 1 bound, xy equal 3, 1 bound. Then I found the multiplication x, y. Then here, see, I got one beautiful bound for you. U is between 1 and 3. So then let's work on these lines. Then what do you have for R1 and R2 and R1? And R2 bounds are these. X, sorry, is x equal y and x equal, I'm sorry, y equal 3x. Y equal 3x. So, see, you have x equal y, right? And you have y equal 3x. Then I will use this because see, my goal is to convert these bounds into bounds in terms of u and v. Okay, then see, then let's use this then for x equal y, because you have x is u over v, and y is v. Then for x equal y, you can say you have this equality, right? Then you can say you have u equal to v squared. U equal to v squared. And what about this one? For this one, the same. For this one, we get the same thing. Because you have y equal 3x, again, same thing. You have yv equal to 3 times uv. Again, if you use cross multiple, you have v squared equal to 3u. V squared equal to 3u. U and y are positive because x and y also is positive. Because here x is positive, y is positive. Then you can say v is positive, u also is positive. Then we can also write this. U and v are positive. Then we have u is between 1 and 3, and here we have v squared equal u, v squared equal 3u. Then one bound here gave me this, another bound gave me this. Any question, please? Any question? Any question? Okay, very good. So, so then see, here you had these bounds, then I use these bounds, I use the given transformation. After all, I found these. U is between 1 and 3, and we have these. V squared equal u, v squared equal 3u. Then I can say in UV plane, my region is between u is between 1 and 3, and we have these two. V squared equal u, v squared equal to 3u. V squared equal u, v squared equal to 3u. So see, if you let me erase this, in my country mostly we write in this way. Then see, we have v squared is between u and 3u. Okay. Okay. I combine them together. So any question, please? Any question? So everybody is following? Okay, then let me erase this. Then by using my calculation, I got these bounds for u. I got these. I got u is between, I'm sorry, yes, u is between 1 and 3. V squared is between u and 3u. U and v are positive. U and v are positive. These are something that I concluded up to. So now we are ready to graph them on UV plane. This is u, this is v. U is between 1 and 3, then 1, 2, 3, this is u. This is u. Then for u, we have 1, 3, 2 lines. Okay, we have also two functions. We have v squared equal u, we have v squared equal 3. Let's see, v squared equal u is a problem. But you know that the problem actually is not this kind of problem. The problem, because here you have, if you want to use y squared, y and x, this is y squared equal x. Then the problem will be something like this. This is v squared equal u. Any question? Any question? Let's see this point, for example, here. This guy is 1, 1. 1, 1. What about this? V squared equal 3u. Again, it is a problem. This problem also passes through origin. But if we put this guy 3, then we get 3. And because, see, if you plug in 3 here, you have 3 times 3 is 9, then v squared equal 9, v squared equal 9, then v equal 3. Then this is 2, this is 3, then we have something like this. Okay, This is v squared equal 3u. If I made a mistake somewhere, let me know. And this is the region. Then when you transform this region into, let me denote this region by S. Then when you transform R, by using that transformation, you will reach to S. This is S. Any question? Any question? Any comment? Any question? Mm-hmm. V squared. Okay. So now we are ready to evaluate this integral. Then with your permission, let me erase this part. Then by using our formula, by using the important change of variable theorem that we had yesterday, you can say this is equal to integral on S. What is S? S is this guy. Such that you need to replace x by function in terms of u and v, and y in terms of function of u and v. We had x equal uv, y equal what? V. And let's do it. We have x, I will replace x by u over v, y by v. So what we need here, as I explained yesterday, we need Jacobian here. I will denote this Jacobian by J, then du dv. It doesn't matter which one first, which one second, because I didn't find out bounds yet. Since here we don't have bounds, then it doesn't matter which one will be written here first, which one is written second. So then what did I do? I replace by this guy, I replace x by u over v, y by v. This transformation is given. What is this j? J here is Jacobian. We have to find Jacobian. As I explained yesterday, Jacobian is this determinant. Jacobian is partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, partial derivative of y with respect to v. Okay, x, v, y, v. Then let's differentiate. Partial derivative of x with respect to u is 1 over v. Partial derivative of x with respect to v is minus u over v squared. Partial derivative of x with respect to u, 0. I'm sorry, partial derivative of y with respect to u, 0. Partial derivative of y with respect to v, 1. And you can find this determinant very easily. Determinant is 1 over v. 1 over v. Any question? Please let me know. Any question? Then Jacobian for this integral here, for this transformation is 1 over v. Then this guy is 1 over v. And see, you replace x by this function, it was given. You replace y by this function, you found Jacobian, and you replace Jacobian again. Question? Question? Okay. So now we are ready to find bounds. Now my goal is to find bounds. So, see, I prefer, it doesn't matter, which integral is labeled by u, which integral is labeled by v, but let's label this guy by v, this guy by u, this guy by v. So, what is bounds for u? U is between 1 and 3. Then, bounds for u is 1, 3. Let me write it better. So, this is u, bound for u is 1, 3. Second one is v. What is bounds for v? For v, see, you have two functions. And here you can see that the first function is this guy, the second function is this guy. But this is v squared equal u. Then since this is v squared equal u, you have v equal to root u. Second one is v squared equal 3u. Then you have v equal to root 3u. Why I didn't write plus minus? Because it is in the first quadrant. The first quadrant, you have v are positive. Then this is root u, root 3u. Root u, root 3u. Any question? Any question? Okay, good, good, good. Good, good, good. Any question? Any comment? Okay. So then this guy is root u, this guy is root 3u. See, I took a square root. Then bound for v or root u, root 3u. Bound for u is 1, 3. Oh my. Okay. So, okay, guys, can I erase Jacobian here? Can I erase Jacobian? Or maybe I can write it here again because maybe somebody. Okay, see, Jacobian was so let me see. The function was x equal v, y equal v. Then for Jacobian we have 1 over v minus uv squared. This is 0, this is 1, then Jacobian is 1 over v. So then let's integrate. You have 1 over 3 root u, root 3u. V and v will be cancelled. You have u over v. dv, du. Then dv, du. This is v. v. So then now we can integrate with respect to v here, and after that we can integrate with respect to u. Any question? It seems to me that if we write first integrate with respect to u, then maybe it would be easier, right? No? See, I label, okay, so let me see. So, see, I wrote u first and v second, right? And here if we integrate with respect to v first, then we need to use, okay, it's okay. We need to use integration by part. It is not a bad exercise. You can actually do exercise. So then okay, I will use Fubini theorem. I will integrate with respect to v first, and after that I will integrate with respect to u second. Okay, so let me erase here. Then I have 1, 2, 3 root u, root 3u, u over v, dv, du. So I will integrate with respect to v first, then you have integral 1 to 3. If you integrate with respect to v, you have u and n of v. This is root u, root 3u, du. Then let's plug in this integral. You have 1, 3 u ln of root 3u minus u ln of root u du. Okay, so see this guy, okay, all of you know that from high school, this guy can be written as 3u to the power of 1/2. This guy also can be written as u to the power of 1/2. And you know that power can be written outside of logarithm. Then this is integral 1/3 u over 2 ln of 3u minus this is u over 2 ln of u. This is du. Okay, I got something nice. I didn't expect that. Okay. So then see u half are in common. Then you can factor them out. Then this guy can be written as u over 2 times ln of 3u minus ln of u. ln of 3u minus ln of u. And from high school, we know that when you have the subtraction between logarithm, you can divide these. Then this is equal to integral 1/3 u half ln of 3u over u du. And u will be cancelled. U and u will be cancelled. You can see you have u half. I factor out u half. Then after that, you have ln of 3u minus ln of u. Then by using fact that we had in high school, maybe, you can divide this. And 3u, and I cancelled u and u. Then what is left? No, we have u have ln of 3. That's an easy integral, but any question up to now? Any question? So, any question? Any question? So I can continue here. Okay, this is 1/2. Then we have this integral. We have 1/3 u half ln of 3 du. ln of 3 is constant, 1/2 is constant, can be written outside, then u du. It is an easy Calc 1 question. Then this is ln of 3 over 2. This is 9 over 2 minus 1/2. Because all of you know that the antiderivative of this guy is u squared over 2. Then we have u squared over 2, you just need to plug it in the function. So 9 minus 1 is 8, 8 over 2 is 4. Then we have 4 ln of 3 over 2, which is 2 ln of 3. Okay. 2 ln of 3. Any question, please? Any question? There was one beautiful usage of change of variable theorem. Again, that as I explained, that's really nice theorem, very powerful theorem. And you can see one usage of that theorem. We change or we transformed the given region into nicer region, and after that we got a nice integral. We found the integral and we received the final answer. Any question? Any question? Any question? Okay, good. So if there is no question about this, I would like to solve one more example. I think 2 examples is enough. But any question? Any comment? So okay. So see, today we will have one extra activity. Please solve this question and write your answer on a piece of paper and scan it and upload it on the general box. So then, let me see. Then extra credit. Extra credit. Then evaluate. Please evaluate this integral x squared y dA on R. R is inside an ellipse. We have ellipse like this. Then equation of the ellipse is 9x squared plus 4y squared equal to 36. Use this transformation. X equal 2u, y equal 3. Use this transformation. This you want to integrate on R here is inside this ellipse. Then use this transformation, find the transform version of this if you use this transformation and if you convert this, you will convert this into a circle. You will convert actually to a unit circle. And after that, use that unit circle and integrate and find the final answer. This is extra credit, then it will be added to your test tree. So then write your solution on a piece of paper, scan it, and upload it on the Dropbox. Okay. So any question? So, Alex, good question. Alex and all, please write your solution. Okay, there is no special due date. Please upload it before the test tree. Please upload it before test tree. You know, there is no special due date for this one. Please upload it before test tree. And you have time. I will add more extra credits. Then you have time to write your solutions and upload it on the Dropbox. Okay. So, guys, can I erase here to write one more question? Okay. So, let me. Okay, I want to use this theorem for another question. Then evaluate this time this integral on R x plus y times e to the power of x squared minus y squared dA. Here R is enclosed by lines, these lines, x minus y equals 0, x minus y equal 2, x plus y equals 0, x plus y equal 3. Let's evaluate this integral. R is enclosed by lines, x minus y equals 0, x minus y equal 2, x plus y equals 0, x plus y equal 2. Actually, here we have this region. This is x, this is y. X minus y equals 0 is this line. X minus y equals 0. We have x minus y equal 2. Then if we set x equals 0, y is negative 2. And if we say y equals, then yes, this is x minus y equal 2. We have x plus y equals 0. This is x plus y equals 0. And x plus y equal 3. We said x equals 3. We have, so let me see, x equals 0, y is 3. And this is 3. Okay, this is x plus y equal 3. And what is the region? R is here. This is R. So then see, we have this region. We want to integrate up this function on this region. And here actually, as you can see, no transformation is given. Then we have to identify what transformation here is appropriate. This question actually is easy. I see you can guess what transformation here is appropriate. How? Because see, when you look at the given region, you can see that you have common equations, which are x minus y, x plus y. Because you can describe this region by using x plus y. You can say x plus y is between 0 and 3. X minus y is between 0 and 2. Okay? If I want to explain this region in a more understandable way, I would say this region is a region which is between x plus y is between 0 and 3, x minus y is between 0 and 2. So then, because I want to define new variables, u and v, I will use these common equations and define u and v. I will say u is x minus y, v is x plus y. Then based on my experience, if you have common equations in the given region, defining that common equation sometimes, like we cannot say always, sometimes will be very appropriate. Then here you can, when you define why I'm saying that it is appropriate, see, if you define u equal x minus y, then you can say bound for u, because x minus y is between 0 and 2, you can say bound for u is between 0 and 2. See? And if you define x plus y is v, because x plus y is between 0 and 3, you can say bound for v is between 0 and 3. Okay? Then when we define u equal x minus y, then clearly we can conclude u is between 0 and 2, based on our assumptions. And when we define v equal x plus v, then again we can conclude v is between 0 and 3. Then what is that? It is a rectangle. Then see, you have this, I can say, oblique rectangle in xy plane, but by using this transformation, you can rotate and make it nicer rectangle. Any question? Any question? See if I delete this. I can say by using this transformation, in UV plane, we have u is between 0 and 2, v is between 0 and 3. You can see we have, this is S. You can see this is a given region. We use this transformation, then we convert into S. Much, much nicer rectangle for sure. Any question? Question? So, and now we are ready to evaluate integrals. So then, let me see, we have, this is integral on S. So I defined u as, so which one was x plus y? Which one was 2? Come on. So I define u as x minus y, v as x plus y. Yes. So then here x plus y is v, then it is v, but e to the power of x squared minus y squared, you know, that can be written as e to the power of x minus y plus x plus y. All of you from high school know that x squared minus y squared is x minus y times x plus y. Then it can be written as e to the power of u times v. We have Jacobian here, and we have du dv. I don't know which one u, which one v, but okay. So, bounds here are clear. Why? Because you are integrating on a rectangle, then it is very easy. 0, 2, 0, 3. Then dv du. Then dv du. The only thing which must be explained is Jacobian. How we can find Jacobian? Do you know what's wrong with Jacobian? See, it is a formula for Jacobian. You have partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of u with respect y with respect to u, partial derivative of y with respect to v. You can use this formula when, like the previous example, when x is given in terms of u and v, y is given in terms of u and v. Then you can find partial derivative and find answer. But here, see, x is not given in terms of u and v. U is given in terms of x and v. I'm sorry, x and u. U is given in terms of x and y. V is given in terms of x and y. But for the previous example, if you look at your note, you will see that for the previous example, x was given in terms of u and v. Then I differentiated and I wrote here what we should do here. Someone can say, what about if we switch u and x? It means we write u with respect to x, u with respect to y, v with respect to x, v with respect to y. Instead of differentiating x with respect to u and y with respect to u and v, what about if we differentiate u with respect to x, v with respect to x, u with respect to y, v with respect to y? Are they the same? No, but they are connected. So then what is the connection between them? Actually, this guy equal to this guy to the power of -1. It means if you find the reciprocal of this, it will be equal to this one. Okay? So is it clear? No, it is not clear. If somebody can prove this for test number 3, I will add 10 points to this student's test number 3. Then we have this extra credit. Then this is not for everyone, for sure. This is for people who want to think a little bit more. Then 10 points to test 3. What must be proved? You need to prove this one. Round off this guy, as you know, is denoted by round off xy, round off uv equal to 1 over round off uv on round off x. Okay. That's a beautiful, very, very nice question. Actually, you will have time to take. What about, because, oh my God, because we have just 1 week for test 3, then maybe we need more time. Okay, this is for final exam. This is for final exam. Then you have time to write your solutions by final exam. 1 month, then we can continue. So, okay, then let me use this. Then now when we want to find Jacobian, since we cannot find Jacobian directly, easily, we can find Jacobian directly, but it is not easy. Easy but time consuming. Then we don't want to find Jacobian directly, then I will find this determinant, and after that I will find the reciprocal of this determinant. That's it. And it is Jacobian. And we can say Jacobian equal to this guy. So then we have x equal u plus v. X equal u plus v. So I'm sorry. We have v equal x plus y, u equal x minus y. Then if we use this, then we can say Jacobian equal to reciprocal of this determinant. Then u with partial derivative of u with respect to x, 1. Partial derivative of u with respect to y, 1. I'm sorry, minus 1. Partial derivative of v with respect to x, 1. Partial derivative of v with respect to y, 1. If you find this integral is 2. But what is Jacobian? Jacobian is reciprocal of 2. The Jacobian is reciprocal of 2. Any question? Any comment? Anything? Then Jacobian is 1/2. Then we can plug in 1/2 here. This guy is 1/2. Okay. So Guys, I know you are tired. I'm sorry. I will finish it. This is yeah. No, it's fine. So okay. So then we have the okay. Okay, I will finish it tomorrow. Then okay, it's not necessary to finish today. Then this is an easy integral. I will integrate this integral tomorrow, and tomorrow I will finish it. Then see, then today we used that theorem of change of variable for double integral for two examples. One example, also I gave you one example to solve. I just want to give you one more extra credit. This extra credit also, please write your solution and upload it on your Dropbox. I will finish this one tomorrow. Then, but let me write this extra credit today, and we are at the end of this section. Another extra credit, then extra credit. Please find this integral r cos of y minus 6 over y plus 6 dA. And r is trapezoid with these vertices. With vertices 1, 0, 2, 0, 0, 2, 0, okay. Then this is another extra credit. Then write your solutions and upload your solution on Dropbox. No due date. Please do it before test 3. And then 2 extra credits for today. One of them is one, and we have this extra credit. This extra credit is not for everyone. It's for people who are more interested. Okay, so any question? Sorry. Any question, any comment, anything, let me know. If no questions, see you all tomorrow and have a good day. I'm sorry, see you all on Monday. Have a good weekend. Oh, hi, Joe. Oh, let me see. Hello, Joe. Did you Joe, did you go home? You are at home now? You want to speak? Can you speak? Joe, can you hear me?
Yep. Can you hear me?
Yes, I can hear you. Oh, Joe, you are at home or you are still in quarantine?
I'm at home now, so it's pretty good.
Great.
Yeah,
Okay, I am very happy. Okay. So, okay, did you see videos on Panopto?
Yeah, right now I can see it. A couple of hours ago, I sent you a picture on my web, but it doesn't work at all. So.
Oh, sorry about that. I didn't see the email. See, in the morning I had exam. Then that exam actually, took a long time because the students didn't know how to use technology and something. Then okay, lots of
it's okay.
okay. Then